Alpha Centauri shimmers 4.37 light-years away. Our nearest stellar neighbor, the closest star system where another Earth might orbit. Scientists have confirmed planets exist there. Engineers have designed spacecraft that could theoretically survive the journey. Physicists have calculated propulsion systems capable of reaching meaningful fractions of light speed. Yet no human being will ever set foot on a world orbiting those distant suns. The reason has nothing to do with rockets or physics or engineering limitations. The truth is far more disturbing. Every proposed mission to Alpha Centauri requires travel times measured in centuries or millennia. And no human civilization in recorded history has ever remained stable for that long. The cosmos has placed our nearest neighbors forever out of reach. If you want to understand why the stars will remain eternally beyond human touch, hit that like button and subscribe. Now, settle down, get yourself comfortable. Let's begin. Look up on any clear night and find the constellation Centaurus. Hidden within that pattern of ancient light lies our closest stellar neighbor, Alpha Centauri, a triple star system containing two sun-like stars locked in orbital embrace, plus a small red dwarf called Proxima Centauri that holds the nearest known exoplanet to Earth. The Alpha Centauri system has captivated astronomers for centuries. The two primary stars, Alpha Centauri A and Alpha Centauri B, orbit each other in a gravitational dance lasting approximately 80 years. Alpha Centauri A burns slightly hotter and brighter than our Sun. A yellow star roughly 10% more massive than the stellar furnace warming Earth. Its light would feel familiar to human eyes. Standing on a planet orbiting Alpha Centauri A, you would see a sun remarkably similar to our own, casting shadows and warming your skin in ways that would feel almost like home. Alpha Centauri B glows orange and cooler, slightly smaller than our Sun but still capable of hosting planetary systems where liquid water could exist. The two stars approach within 11 astronomical units of each other at their closest and separate to 36 astronomical units at their most distant. From a planet orbiting either star, the companion would appear as an extraordinarily brilliant point of light, sometimes bright enough to cast shadows of its own and read by at night. Proxima Centauri, the third member of this stellar family, lies much farther from its companions. This tiny red dwarf orbits the central pair at a distance of approximately 13,000 astronomical units. 1 astronomical unit equals the distance from Earth to our Sun. Proxima Centauri is so far from its stellar siblings that it requires over 500,000 years to complete a single orbit around them. Despite this enormous separation, the three stars are gravitationally bound, traveling together through the galaxy as a single system. Scientists confirmed in 2016 that Proxima Centauri hosts at least one planet orbiting within its habitable zone. This world, called Proxima Centauri B, receives enough stellar warmth that liquid water could theoretically exist on its surface. The discovery electrified astronomical communities worldwide. Here was a potentially habitable planet orbiting the very nearest star to our solar system. The cosmos had placed a possible second Earth right next door in astronomical terms. Proxima Centauri B orbits its parent star once every 11.2 Earth days. The planet lies far closer to Proxima Centauri than Mercury lies to our Sun, completing its tight orbit at a distance of only 7 million kilometers. But because Proxima Centauri burns so much cooler than our star, this close orbit places the planet squarely within the zone where temperatures permit liquid water. The planet masses approximately 1.3 times Earth's mass. Rocky and terrestrial rather than gaseous like Jupiter or Neptune. A world you could theoretically stand upon and gaze up at an alien sky. The conditions on Proxima Centauri B remain tantalizingly uncertain, the planet likely tidally locked to its star, presenting the same face eternally toward the dim red sun, while the opposite hemisphere freezes in permanent darkness. Between these extremes, a twilight zone might harbor temperatures suitable for life as we understand it. Oceans could potentially exist in this ring of eternal dusk, where the light never fully rises and never fully sets. Red dwarf stars like Proxima Centauri are prone to violent flares that could strip away planetary atmospheres and sterilize surfaces with intense radiation. Whether Proxima Centauri b has retained an atmosphere thick enough to protect potential life remains unknown. The planet might be a barren, irradiated rock, or it might harbor conditions favorable to biology. We cannot know without visiting, or at minimum sending instruments capable of analyzing its atmospheric composition from close range. Additional observations suggest Proxima Centauri may host other worlds as well. A candidate planet designated Proxima Centauri that C might orbit farther out, completing one revolution every 5.2 years. Another possible world, Proxima Centauri d, might exist even closer to the star than Proxima b. The Alpha Centauri system potentially contains multiple worlds awaiting exploration. An entire planetary system lies at our cosmic doorstep, begging to be explored and studied, and perhaps someday visited. This is why Alpha Centauri matters so profoundly to discussions of interstellar travel. If we cannot reach Alpha Centauri, we cannot reach anything. Every other star lies farther away. Every other potentially habitable world requires longer journeys. Alpha Centauri represents the minimum possible challenge for interstellar travel. If this destination proves impossible, all destinations prove impossible. The distance to this cosmic neighbor measures 4.37 light-years. Light itself, traveling at 670 million miles per hour, requires more than 4 years to cross the void between our Sun and Alpha Centauri. A beam of light departing Earth tonight will not arrive at Proxima Centauri until nearly 4.5 years from now. That distance sounds manageable when expressed in light-years. The number 4 seems small enough to comprehend. Humans routinely plan projects spanning 4 years. University degrees require 4 years. Presidential terms last 4 years. Olympic cycles measure 4 years. Surely a civilization capable of sustained 4-year efforts could manage an interstellar journey. But converting this cosmic measurement into human terms reveals the true horror of interstellar separation. 4.37 light-years equals approximately 25 trillion miles. Written out completely, this number requires 13 digits. 25 followed by 12 zeros. The human mind cannot genuinely comprehend such distances. We evolved to understand distances we could walk in a day or perhaps travel over a lifetime. Continental scales already exceed our intuitive grasp. Interstellar distances exist in a realm of pure mathematical abstraction. Consider a more tangible comparison. If you could drive a car at highway speeds toward Alpha Centauri, maintaining 65 miles per hour continuously without stopping for fuel or rest, the journey would require approximately 44 million years. 44 million years ago, dinosaurs still ruled the Earth. Mammals were small creatures hiding in shadows, waiting for an asteroid to clear the stage for their eventual dominance. The entire evolutionary journey from those tiny mammals to modern humans would fit within the driving time to our nearest stellar neighbor. Commercial aircraft traveling at 600 miles per hour would require approximately 4.7 million years to reach Alpha Centauri. The fastest bullet ever fired from a conventional firearm would need roughly 300,000 years. Every mode of transportation humans have ever invented requires timescales measured in hundreds of thousands to millions of years to cross this cosmic gap. Consider the fastest object humans have ever built. The Parker Solar Probe currently holds the record for maximum spacecraft velocity. At its closest approach to the Sun, this spacecraft reaches speeds exceeding 430,000 miles per hour. This velocity seems impossibly fast by earthly standards. A vehicle traveling at such speeds could circle Earth in less than 4 minutes. It could reach the Moon in approximately 30 minutes. It could cross the Atlantic Ocean in roughly 20 seconds. Yet, even at this record-breaking velocity, the journey to Alpha Centauri would require approximately 6,700 years. A spacecraft departing Earth today at Parker Solar Probe speeds would arrive at our nearest stellar neighbor around the year 8700. That time span exceeds the entire length of recorded human history. Every civilization that has ever existed from ancient Sumer through modern nation-states would fit within the journey of time to our closest cosmic neighbor. The Great Pyramids of Giza were constructed approximately 4,500 years ago. Stonehenge was erected roughly 5,000 years ago. The earliest known written records date to approximately 5,000 years before the present day. Human beings have maintained recognizable civilizations for roughly 6,000 years. The journey to Alpha Centauri at our fastest achieved velocities would require more time than humans have been building cities. When construction began on the Great Pyramid of Giza, a spacecraft departing at Parker's solar probe, velocities would not yet have traveled 1% of the distance to Alpha Centauri. When Rome fell, that same spacecraft would have covered perhaps 1.5% of the journey. When Columbus reached the Americas, it would have traveled less than 2%. Today, after the rise and fall of every empire in human history, it would remain less than 3% of the way to our nearest stellar neighbor. But the Parker Solar Probe achieves such extreme velocities only through gravitational assists from the Sun. The spacecraft does not carry engines powerful enough to reach such speeds independently. Instead, it falls toward the Sun using our star's immense gravity to accelerate to record-breaking velocities. No spacecraft traveling outward from our solar system can maintain such speeds. The actual velocities achieved by interstellar-bound probes are far more modest. Voyager 1, launched in 1977, currently holds the record as the most distant human-made object. This remarkable spacecraft has traveled farther from Earth than any other human creation in history. After more than 4 decades of travel, Voyager 1 has covered approximately 14 billion miles from its launch point. That sounds impressive. Until you realize, Voyager 1 has traversed less than 0.06% of the distance to Alpha Centauri, less than 0.1% of the journey to our nearest stellar neighbor. At its current velocity of roughly 38,000 miles per hour, Voyager 1 would require approximately 70,000 years to reach Alpha Centauri. 70,000 years. Modern humans began their major migration out of Africa approximately that long ago. The entire span of human migration, across continents and development of language, and invention of agriculture and rise and fall of every civilization in history, would fit within the journey time required for our fastest outbound spacecraft to reach the closest star. 70,000 years ago, humans had not yet reached Europe. The cave paintings at Lascaux would not be created for another 50,000 years. Agriculture would not be invented for another 60,000 years. Writing would not emerge for another 65,000 years. Everything that humans have ever accomplished in art, science, technology, culture, and philosophy has occurred within a time span shorter than Voyager 1 would need to reach Alpha Centauri. This brings us to the fundamental problem that renders interstellar travel impossible for human beings. The timescales involved exceed not just individual human lifespans, but the demonstrated stability limits of human civilization itself. Confirmed historical analysis reveals a disturbing pattern. No human civilization has ever maintained continuous coherent existence for more than a few thousand years. The longest-lived stable political entities in human history survived approximately 2,000 years before fragmenting, collapsing, or transforming beyond recognition. Most civilizations endure far shorter periods. Empires rise and fall within centuries. Nation-states reorganize within decades. Political systems that seemed eternal to those living within them vanish within generations. The Roman Empire, from its legendary founding to the fall of Constantinople, spanned roughly 2,000 years, but included radical discontinuities that challenge any notion of true continuity. Ancient Egypt maintained cultural continuity for over 2 millennia, but experienced intermediate periods of chaos and foreign domination. Chinese civilization claims continuous cultural identity spanning 4,000 years, but this continuity masks constant political upheaval, with the average dynasty lasting roughly 300 years before collapse. A journey to Alpha Centauri using current technology requires 70,000 years. Even the most optimistic propulsion concepts ever seriously proposed still require centuries to millennia of travel time. No human civilization has demonstrated the capacity to maintain coherent existence across such timescales. Consider what 70,000 years means in terms of human social evolution. No written records exist from that era. We know almost nothing about the social structures, religious beliefs, or cultural practices of humans from that period. The archaeological record provides only fragmentary physical evidence of daily life. A mission launched 70,000 years ago by our distant ancestors would be arriving at Alpha Centauri today. The civilization that launched it would be utterly unrecognizable. The language spoken at launch would have evolved beyond comprehension. The political structures would have transformed countless times. Every aspect of human existence would have changed beyond recognition. Who would receive the returning data? What civilization would claim the achievement? What institutions would even remember the mission was launched? This is not merely a technical problem awaiting a clever solution. This is a fundamental constraint imposed by the nature of human social organization, combined with the physics of interstellar distance. We cannot engineer our way around civilization instability any more than we can engineer our way around the speed of light. Engineers and physicists have proposed numerous advanced propulsion concepts that could theoretically reduce interstellar journey times. Nuclear pulse propulsion using controlled atomic explosions could achieve velocities of 3 to 5% of light speed. Antimatter engines offer theoretical maximum velocities approaching 30% of light speed. Laser sail systems using powerful ground-based lasers could accelerate tiny probes to 20% of light speed. Ion drives could theoretically achieve velocities far exceeding chemical rockets given sufficient time for acceleration. Let us examine the most optimistic scenario seriously proposed by mainstream physics. A spacecraft accelerating at one gravity continuously for a year would reach approximately 90% of light speed. Relativistic effects would compress the subjective journey time for passengers aboard such a vessel. A trip to Alpha Centauri might feel like only a few years to those aboard while decades passed on Earth. But this scenario requires technology so far beyond current capabilities that it belongs more to science fiction than engineering reality. Continuous one-gravity acceleration requires either impossibly efficient fuel or impossibly powerful external propulsion systems. No physical mechanism currently understood could provide such sustained acceleration across interstellar distances. The fuel requirements alone render continuous acceleration impossible. Chemical rockets achieve exhaust velocities of roughly 4 kilometers per second. Reaching even 1% of light speed using chemical propulsion would require fuel masses exceeding the mass of the observable universe. Nuclear thermal rockets improve exhaust velocities by roughly a factor of 2, still nowhere near sufficient for interstellar travel. Even fusion, propulsion, the holy grail of space travel enthusiasts, cannot solve this problem. Theoretical fusion rockets could achieve exhaust velocities of perhaps 10,000 kilometers per second. This represents an enormous improvement over chemical or nuclear thermal propulsion. Yet reaching 50% of light speed would still require fuel masses thousands of times greater than payload masses. The mathematics simply do not support continuous acceleration to relativistic velocities. More realistic, advanced propulsion systems offer less dramatic improvements. Nuclear pulse propulsion, as designed for Project Orion in the 1960s, could theoretically achieve 3% of light speed. This design used small nuclear bombs detonated behind a massive pusher plate to accelerate the spacecraft. Each explosion would add incremental velocity. Thousands of bombs would eventually push the vessel to interstellar speeds. At 3% of light speed, the journey to Alpha Centauri would require approximately 140 years. 140 years represents a more approachable timescale than 70,000 years. Several human lifetimes rather than the entire span of human existence. Generation ship concepts propose launching spacecraft designed to support multiple generations of travelers who would live and die aboard the vessel during the journey. Children born during the voyage would grow old and die in space. Their grandchildren would raise great-grandchildren who might never know they were traveling. Finally, after 140 years, the descendants of the original crew would arrive at Alpha Centauri, having never known Earth firsthand. This approach shifts the problem from individual human lifespans to civilization continuity in an even more constrained environment. A generation ship represents a tiny isolated civilization cut off from Earth and all human support structures. This miniature society must maintain itself for 140 years or more, while traveling through the most hostile environment imaginable. The ship must provide food, water, and air for multiple generations. Closed-loop life support systems must function flawlessly for longer than any mechanical system has ever operated continuously. Social structures must remain stable despite complete isolation from the broader human community. Educational systems must transmit knowledge and skills across generations. Governance structures must prevent the conflicts that tear apart every human society. Eventually. But even this optimistic scenario assumes that the civilization launching the ship remains stable enough to develop the technology, accumulate the resources, and maintain the institutional commitment required for such a project. Building an interstellar spacecraft would require decades of sustained effort, drawing on the resources of entire nations, or perhaps the entire planet. Consider the institutional timescales involved. The Manhattan Project that developed atomic weapons required approximately 4 years and employed over 125,000 workers. The Apollo program that landed humans on the moon spanned roughly 11 years and consumed approximately 4% of the federal budget at its peak. These represent the largest concentrated scientific and engineering efforts in human history. An interstellar mission would dwarf both projects combined. Developing the propulsion technology alone would require decades of sustained research. Nuclear pulse propulsion was studied for roughly a decade before being abandoned due to treaty restrictions and funding cuts. Fusion propulsion has been researched for over 70 years without producing a working reactor suitable for spacecraft. Antimatter propulsion exists only as theoretical proposals, with no clear path to practical implementation. Building the spacecraft would require manufacturing capabilities that do not currently exist. A generation ship large enough to support a viable human population would need to mass millions of tons. No launch system ever built could lift such masses to orbit. Assembly would need to occur in space over many years. The infrastructure to support such assembly does not exist and would itself require decades to construct. Accumulating sufficient fuel would require industrial processes on scales never attempted. Current global nuclear weapons stockpiles would provide barely enough material. Manufacturing additional devices while maintaining the precision required for propulsion rather than destruction would require new facilities and new production lines. Training the crew and developing the closed-loop life support systems would require additional decades of preparation. No human has ever lived in a truly closed ecological system for more than 2 years. Every attempt to create self-sustaining artificial biospheres has experienced critical failures within months or years. Extending these capabilities to 140 years of continuous operation represents an unsolved engineering challenge. From initial concept to launch an interstellar mission would require at minimum 50 to 100 years of sustained civilizational commitment. This timeline must remain stable through political transitions, economic fluctuations, wars, pandemics, and every other disruption that human societies routinely experience. The historical record offers no evidence that such sustained commitment is possible. The United States abandoned lunar exploration less than 4 years after the first moon landing. Apollo 17 returned from the moon in December 1972. By 1975, the Saturn V production lines had been dismantled. The tooling was destroyed, the expertise dispersed. Within a decade of the greatest exploratory achievement in human history, the capability to repeat it had been deliberately erased. Funding priorities shifted. Political will evaporated. The Cold War competition that motivated Apollo wound down. The public lost interest. Other problems demanded attention. The technological capability to send humans to the moon was dismantled and would require decades and hundreds of billions of dollars to rebuild. The superconducting super collider was approved for construction in 1987. This particle accelerator would have been the largest scientific instrument ever built. Billions of dollars were spent. Miles of tunnel were excavated. Then in 1993, Congress cancelled the project. Changing political priorities and cost overruns doomed what would have been transformative scientific infrastructure. The space shuttle was designed to make space access routine and affordable. Instead, it proved expensive and dangerous. 2 shuttles were lost with all crew members. The program was cancelled in 2011 after 30 years of operation. Replacement capabilities took over a decade to develop. If human civilization cannot maintain commitment to reaching the moon for even a decade, what evidence suggests we could sustain an interstellar program for a century or more? This brings us back to the real limitation that haunts every serious analysis of interstellar travel. Technology can theoretically solve propulsion problems. Engineering can theoretically design spacecraft capable of surviving interstellar journeys. Physics permits velocities that would reduce travel times to centuries rather than millennia. But none of this matters if the civilization supporting the mission cannot remain stable long enough to launch it. And none of it matters if the civilization maintaining communication and providing ongoing support cannot survive the journey duration. The mission requires tracking stations that must operate for 140 years. Ground controllers must monitor spacecraft systems and respond to emergencies across timescales exceeding any continuous institutional operation in human history. Communication systems must survive wars and economic collapses and political transitions. Funding must flow continuously through budget cycles and economic depressions and changes in governing philosophy. None of these requirements have ever been met by any human institution for the timescales involved. The oldest continuously operating institutions in human existence are religious organizations and a handful of universities. Even these have experienced massive transformations over centuries. The Catholic Church of 2025 bears little organizational resemblance to the Catholic Church of 1025. No matter how advanced the technology becomes, the fundamental constraint remains unchanged. Interstellar distances require timescales that exceed demonstrated human civilization stability. We are attempting to solve an engineering problem that is actually a social and political problem with no known solution. The gap between Alpha Centauri and Earth represents more than physical distance. It represents a chasm between human organizational capacity and cosmic scale. The universe has placed our nearest neighbors at distances that require journey times exceeding our demonstrated ability to maintain coherent civilization. This is not a puzzle awaiting a clever solution. This is a boundary condition written into the relationship between physics and human nature. The cosmos operates on timescales that dwarf human institutional capacity. The distances between stars require commitments that exceed human organizational stability. Every analysis eventually confronts this same barrier. The engineering can be optimized. The physics can be pushed toward theoretical limits. The propulsion systems can be improved by orders of magnitude. And still the civilization continuity problem remains unsolved. But perhaps technology can still offer escape routes. Perhaps generation ships designed as self-sustaining colonies can bypass the need for Earth-based support. Perhaps cryogenic suspension can freeze passengers through the journey, eliminating the need for multi-generational survival. Perhaps artificial intelligence crews can operate spacecraft without biological limitations. Perhaps revolutionary breakthroughs can compress journey times to decades rather than centuries. The next section examines every proposed technological solution and reveals why each one ultimately fails against the same immovable barrier. no technology can substitute for civilization continuity. No engineering can compress time sufficiently to bring interstellar distances within human organizational reach. Every serious proposal for interstellar travel attempts to solve the timescale problem through technological means. Engineers have proposed ingenious solutions designed to either reduce journey times or extend the functional duration of spacecraft and their occupants. Each approach represents genuine creativity applied to an extraordinarily difficult problem. Brilliant minds have devoted careers to finding ways around the cosmic distances that separate us from even our nearest stellar neighbors. Yet every proposed solution ultimately collapses back into the same fundamental constraint. Interstellar distances require journey times that exceed human civilization stability. No technology can compress time sufficiently or extend civilization durability enough to bridge this gap. The solutions fail not because the engineering is flawed, but because the underlying problem is not truly an engineering problem at all. Let us examine each major approach and trace precisely how it fails against the immovable barrier of civilization continuity. Project Orion, developed during the 1950s and 60s, proposed using controlled nuclear explosions to accelerate spacecraft. The concept emerged from some of the finest engineering minds of the atomic age. Freeman Dyson and Ted Taylor led a team that produced detailed designs for spacecraft propelled by sequential nuclear detonations. Small atomic bombs would be ejected behind the vessel and detonated in sequence. A massive pusher plate would absorb the explosive force and convert it into forward momentum. Shock absorbers would smooth the repeated impulses into continuous acceleration. The physics actually works. Calculations confirmed that nuclear pulse propulsion could theoretically achieve velocities between 3 and 10% of light speed. The energy density of nuclear explosives vastly exceeds chemical fuels. Where chemical rockets achieve exhaust velocities of a few kilometers per second, this represents an improvement of roughly 3 orders of magnitude over conventional rocketry. At 5% of light speed, a spacecraft could reach Alpha Centauri in approximately 87 years. The original Orion designs were more modest, aiming for perhaps 3% of light speed, which would require roughly 140 years for the journey. Either timescale seems to approach practical possibility when compared to the 70,000 years required by current spacecraft velocities. 87 years spans longer than typical human lifespans but remains within conceivable multi-generational planning horizons. A mission launched by young adults might arrive when their grandchildren reached old age. Parents could watch their children depart, knowing that their great-grandchildren might walk on worlds orbiting Alpha Centauri. This timescale seems almost manageable in human terms, but examine what 87 years actually requires from both the spacecraft and the civilization that launches it. The spacecraft must function continuously for nearly a century without major failures. Every mechanical system must either operate flawlessly for 8 decades or be repairable using only resources available aboard. Every electronic component must survive cosmic radiation and thermal cycling that would destroy equipment designed for terrestrial or even orbital environments. The pusher plate must absorb thousands of nuclear detonations without structural fatigue. The shock absorbers must maintain precise calibration across decades of continuous operation. No human-built machine has ever demonstrated such durability under operating conditions. The longest operating spacecraft in history have functioned for roughly 50 years and have experienced numerous system failures requiring workarounds and adaptations. Voyager 1 continues transmitting data, but operates on backup systems with degraded capabilities. Many of its original instruments have failed entirely. The spacecraft survives through redundancy and clever engineering rather than through inherent durability. An interstellar vessel cannot rely on ground controllers to devise workarounds for failing systems. Communication delays measured in years render real-time problem-solving impossible. Every potential failure mode must be anticipated during design. More critically, the launching civilization must maintain the institutional structures necessary to track the mission and maintain communication for 87 years. Ground-based facilities must operate continuously across nearly a century. Personnel must be trained across multiple generations to interpret telemetry and respond to mission events. Funding must remain stable through economic cycles and political transitions that historically have disrupted far shorter programs. Consider what happened to scientific infrastructure built in the 20th century. The Arecibo Observatory in Puerto Rico operated for 57 years as one of the world's premier radio telescopes. For decades, it supported cutting-edge research in radio astronomy and served as humanity's primary tool for transmitting messages to potential extraterrestrial civilizations. Then in 2020, the instrument platform collapsed into the dish below. Decades of deferred maintenance and inadequate funding had weakened the cables supporting the massive structure. One of humanity's windows to the cosmos closed because institutions could not maintain commitment across merely 6 decades. An 87-year mission requires support infrastructure that demonstrates greater durability than any scientific facility in human history. The tracking stations must survive. The communication networks must persist. The institutional knowledge must transfer across generations of personnel. The political will must endure through changes in government and shifts in public priorities. And this assumes everything else works perfectly, which brings us to deeper problems with nuclear pulse propulsion specifically. The technology requires thousands of nuclear devices precisely engineered for propulsion rather than destruction. These are not ordinary nuclear weapons. Each charge must detonate with exact timing and yield to produce optimal thrust. Manufacturing this quantity of specialized atomic bombs would require industrial infrastructure that currently does not exist. New production facilities would need to be designed, built, and operated for years before sufficient propulsion charges accumulated. International treaties prohibit nuclear weapons in space. The Partial Nuclear Test Ban Treaty of 1963 banned nuclear explosions in space, effectively killing Project Orion before any prototype could be tested. Even if one nation decided to withdraw from these treaties, political opposition from other nations would likely prove insurmountable. The prospect of launching thousands of nuclear devices through Earth's atmosphere would face resistance from populations concerned about launch failures, scattering radioactive material across populated regions. Even if all political obstacles vanished, the technical challenges remain staggering. Each explosion must occur at precisely calculated intervals. Timing errors measured in milliseconds could damage the pusher plate or destabilize the spacecraft attitude. The crew compartment must be shielded against radiation that would kill unprotected humans within hours. The mass of this shielding reduces payload capacity and increases the number of propulsion charges required. No prototype has ever been built. No test has ever been conducted. The entire concept remains theoretical after more than 60 years of discussion. The physics works on paper, but no one has ever validated the engineering through actual hardware. All of this still fails because even perfect nuclear pulse propulsion requires journey times measured in decades. The launching civilization must remain stable not just during the journey but during the decades of development preceding launch. The total civilizational commitment spans well over a century, from initial research through technology development, through spacecraft construction, through launch, through journey completion, requires sustained focus, exceeding anything in human history. Nothing in the historical record suggests such sustained focus is possible. Antimatter represents the most energetic fuel conceivably available for spacecraft propulsion. When matter and antimatter contact each other, they annihilate, completely converting their combined mass into pure energy, according to Einstein's famous equation. This reaction releases roughly 100 times more energy per unit mass than nuclear fusion, and billions of times more energy than chemical combustion. Theoretical antimatter rockets could achieve velocities approaching 30% of light speed. A round trip might be completed within a single human lifetime. Passengers departing Earth in their 20s could return in their 60s, having visited another star system and potentially walked on alien worlds. This timeline seems almost routine compared to the centuries required by other propulsion concepts. But antimatter propulsion faces practical obstacles that render it effectively impossible with any technology humans can currently envision. First, consider the problem of production. Creating antimatter requires particle accelerators that consume vastly more energy than the antimatter contains. The process operates at efficiencies measured in billionths of a percent. Current global antimatter production amounts to approximately 10 nanograms per year. All the antimatter ever produced by human technology would not provide enough energy to boil a cup of water. A single interstellar mission would require tons of antimatter. At current production rates, accumulating sufficient antimatter would require longer than the current age of the universe. The entire lifetime of our solar system would not provide enough time to manufacture the fuel for one interstellar voyage using existing production methods. Even if production rates improved by factors of billions, the storage problem remains unsolved. Antimatter annihilates on contact with ordinary matter. A single atom of antihydrogen touching a single atom of regular hydrogen releases enough energy to be detectable by sensitive instruments. Containing macroscopic quantities of antimatter requires magnetic confinement systems that must operate flawlessly for years or decades. Any momentary failure in containment results in catastrophic annihilation that would destroy the spacecraft and everything aboard. No such containment systems have ever been built at scales relevant to spacecraft propulsion. Laboratory experiments have confined individual antiparticles for periods measured in minutes. Scaling from individual particles to tons of antimatter represents an engineering challenge, roughly equivalent to scaling from a campfire to a star. The underlying physics may permit it, but no clear path exists from current capabilities to practical implementation. But suppose miraculous breakthroughs solved both production and storage problems. Suppose antimatter could be manufactured efficiently and contained reliably. Suppose an antimatter-powered spacecraft actually launched toward Alpha Centauri. The 15-year journey time seems almost manageable compared to other proposals. Yet those 15 years still require a spacecraft that functions continuously without the possibility of repair or resupply from Earth. Every navigation system must maintain accuracy across trillion-mile distances, where tiny errors compound into massive deviations. Every radiation shield must protect the crew against cosmic rays and solar storms from Alpha Centauri itself during approach. And the launching civilization must remain stable enough to receive the returning spacecraft. Consider what 15 years means in human political terms. Governments change. Priorities shift. The agency that launched the mission might not exist when the spacecraft returns. The nation that funded it might have fragmented into competing successor states. The economic system that made the investment possible might have collapsed and been replaced by something entirely different. The past century demonstrates how rapidly political conditions transform. 30 years ago, the Soviet Union still existed as a superpower, capable of challenging American dominance. 50 years ago, the United States was withdrawing from Vietnam amid social upheaval that threatened national coherence. A century ago, the British Empire still dominated global affairs, yet would soon begin its rapid dissolution. Human political stability, across even modest timescales, offers little confidence for mission success. This brings us back to the real limitation that haunts every analysis. The civilization supporting the mission must survive the mission duration. Historical evidence suggests this is far less certain than the engineering challenges that consume most discussions of interstellar travel. Breakthrough Starshot, proposed in 2016, represents perhaps the most creative approach to reducing interstellar journey times. Rather than carrying fuel, the spacecraft would ride a beam of light generated by enormous ground-based laser arrays. The concept emerged from the recognition that carrying fuel imposes fundamental limits on achievable velocities. Every kilogram of fuel added to a spacecraft requires additional fuel to accelerate that kilogram. This tyranny of the rocket equation constrains all propulsion systems that carry their own energy source. The concept works by accelerating extremely small probes using radiation pressure from powerful laser beams. Light carries momentum. When photons strike a reflective surface, they transfer that momentum to the object. By reducing spacecraft mass to mere grams and applying tremendous laser power, the probes could theoretically reach 20% of light speed. At this velocity, Alpha Centauri lies merely 21 years away. The Breakthrough Starshot initiative has attracted serious scientific attention and significant private funding. Yuri Milner committed $100 million to initial research. Stephen Hawking endorsed the concept before his death. Serious scientists at major institutions have published detailed analyses of the requirements and challenges. The underlying physics appears sound. Calculations suggest that with sufficient laser power, tiny probes could indeed achieve relativistic velocities. The probes would accelerate for only minutes, while within range of the laser array, then coast for 2 decades before arriving at Alpha Centauri. But trace the requirements carefully, and the civilization continuity problem reasserts itself. The laser array would need to generate approximately 100 gigawatts of power, focused through kilometer-scale optics. 100 gigawatts exceeds the total electrical generating capacity of most nations. Building such a facility would require decades of construction and hundreds of billions of dollars in investment. The optical systems would need to maintain alignment precision measured in fractions of wavelengths across kilometer baselines. No optical system of comparable scale and precision has ever been constructed. Operating the laser array would require energy infrastructure and maintenance systems spanning the 20-plus year mission duration. The ground facilities cannot be mothballed after launch. They must continue operating to provide tracking data and potentially to communicate with the probes. Personnel must be trained and retained across decades. Funding must flow continuously through budget cycles and political transitions. The probes themselves weigh only grams, which severely constrains scientific instrumentation. A few grams cannot carry cameras capable of resolving surface features on distant planets. A few grams cannot carry spectrometers capable of analyzing atmospheric composition. A few grams cannot carry communication systems capable of transmitting useful data across 4 light years. The power required for interstellar communication vastly exceeds what gram-scale solar panels could provide. More fundamentally, the probes cannot slow down. They carry no propulsion systems. They would flash through the Alpha Centauri system at 20% of light speed, having no ability to enter orbit or land on any planetary surface. The encounter would last mere hours after 20 years of travel, a brief glimpse followed by eternal departure into the void beyond. No humans would travel aboard gram-scale probes. Laser sails offer no path to crewed interstellar missions. They represent at best a reconnaissance approach that requires sustained civilization commitment across multiple decades for minimal scientific return. A civilization capable of such sustained commitment might learn basic facts about the Alpha Centauri system. It would not achieve human presence among the stars, and the laser facility itself demands institutional stability that human societies have never demonstrated. The skilled workforce must be maintained across generational transitions as older engineers retire and younger engineers must be recruited and trained. The funding must survive political changes and economic disruptions that historically have derailed far less ambitious projects. If individual humans cannot survive interstellar journey times, perhaps human communities can. Generation ship concepts propose building spacecraft large enough to support self-sustaining populations across centuries of travel. This approach accepts that no individual will complete the journey. Instead, the mission becomes a multi-generational project where children are born and elders die, while the ship travels ever onward toward its distant destination. The mathematics seem straightforward on first examination. Build a vessel containing a few hundred to a few thousand people. Provide closed-loop life support systems that recycle all air, water, and nutrients indefinitely. Include genetic diversity sufficient to maintain healthy populations across generations. Establish educational systems to transmit knowledge and skills to each new generation. Launch toward Alpha Centauri and let the descendants of the original crew complete the journey their ancestors began. At nuclear pulse propulsion velocities of 3 to 5% of light speed, the journey would require roughly 100 to 150 years. Perhaps 4 to 6 generations would live and die aboard the vessel before arrival. The founding crew would never see Alpha Centauri, but their great-great-grandchildren might walk on worlds orbiting distant suns. Generation ships represent perhaps the most thoroughly analyzed approach to interstellar travel. Countless studies have examined population dynamics and minimum viable population sizes. Researchers have analyzed life support requirements and closed ecological system design. Sociologists have proposed governance structures for multi-generational voyages. Every serious analysis reveals the same fundamental problem. Generation ships require maintaining a stable, isolated civilization for longer than any isolated human community has ever survived. Consider the historical record of small, isolated human populations. Island communities consistently experience genetic founder effects within a few generations. Limited gene pools lead to increased expression of recessive disorders. Inbreeding depression reduces fertility and increases mortality. Populations that seem stable over decades reveal accumulated genetic damage over centuries. The Pitcairn Islanders, descended from the Bounty mutineers, provide a cautionary example. The isolated community experienced severe population pressures and resource depletion on their tiny island, leading the British government to relocate them to Norfolk Island in 1856. The population had experienced significant genetic and social strain within just a few generations. A generation ship crew would face similar pressures across the century-plus voyage, with no possibility of introducing new genetic material from outside populations or relocating to escape resource constraints. Closed religious communities fragment through schism and defection, even when bound by intense shared ideology and external pressure that reinforces group identity. The Shakers, who once numbered thousands across 19 communities, have dwindled to a handful of elderly members. Their celibate lifestyle prevented natural reproduction, but the pattern of decline through defection and schism appears in reproducing communities as well. Utopian communities from Brook Farm to Jonestown have collapsed within decades despite the passionate commitment of founding members. The biosphere. Two Experiment in Arizona provides a particularly relevant cautionary tale. 8 people attempted to live in a sealed ecological system for 2 years. The project experienced oxygen depletion, requiring external intervention. Crop failures threatened food supplies. The crew split into hostile factions that stopped speaking to each other. After just 2 years in isolation, the social fabric had nearly disintegrated. A generation ship would need to maintain cohesion for 50 to 75 times longer. Arctic and Antarctic exploration parties provide perhaps the most relevant historical analogues for generation ship conditions. Small groups of humans isolated in hostile environments with no possibility of external assistance and limited resources that must be carefully managed. The historical record is grim. Conflicts emerge within months of isolation. Leadership disputes fracture groups into competing factions. Competition for scarce resources breeds resentment that festers into open hostility. Without external pressure to maintain cooperation, internal tensions tear communities apart. The Donner Party survived mere months before descending into cannibalism and murder. Antarctic expeditions have experienced mutiny and violence within single years of isolation. The Greely expedition to the Arctic lost 19 of 25 members to starvation and violence during a single winter when their resupply ship failed to arrive. The psychological pressures of confinement and isolation reliably produced dysfunction in groups that seemed healthy and cooperative at departure. A generation ship would constitute the most extreme isolation in human history. No external contact would be possible beyond radio signals, requiring years for round-trip communication. No resupply ships could bring fresh provisions or replacement equipment. No immigration could refresh gene pools or introduce new perspectives to break intellectual stagnation. No emigration could remove dissidents or provide escape valves for the discontented. No external authority could adjudicate disputes or enforce agreements between hostile factions. The psychological stresses alone would likely prove fatal to mission success across century-plus timescales. Our minds expect change and novelty, and the possibility of escape from unpleasant situations. Generation ship inhabitants would spend their entire lives within enclosed spaces of fixed dimensions. The same corridors walked daily for decades, the same faces encountered at every turn, the same artificial lighting and recycled air, an unchanging routine stretching across lifetimes. Studies of long-duration space missions reveal severe psychological effects from isolation and confinement, even in carefully selected astronauts who volunteered for the experience. Depression affects significant percentages of crew members on missions lasting merely months. Interpersonal conflicts emerge despite extensive psychological screening and continuous contact with Earth. Sleep disorders and cognitive impairment accumulate over extended missions. Generation ships would multiply these stresses across lifetimes, while eliminating the external support that helps current astronauts cope. The problem of purpose compounds across generations in ways that doom multi-generational missions. The founding crew chose to undertake the mission. They believed in the goal. They accepted the sacrifices. They made an informed decision to spend their lives traveling toward a destination they would never reach. Their commitment sustained them through hardship, but their children did not choose. They were born into a metal tube hurtling through void. They never walked under open sky, or swam in oceans or climbed mountains. They know Earth only through recordings and stories told by elders, who themselves may never have experienced planetary life. Why should they sacrifice their only lives for a destination their grandparents chose and they will never see? The third generation has even less connection to the original mission. Earth becomes mythology. Alpha Centauri becomes abstraction. The journey becomes simply existence. Why maintain systems for a goal that means nothing to those doing the maintaining? Why follow rules established by people dead for decades? Why not redirect the ship's resources toward immediate comfort rather than eventual arrival? By the fourth or fifth generation, the original mission may be entirely forgotten or actively rejected. Shipborne populations might develop ideologies that view the journey itself as sacred and arrival as apostasy. Factions might fight over whether to continue toward Alpha Centauri, or turn back toward a mythologized Earth, or simply stop and drift forever through the void. The social dynamics that tear apart earthly civilizations would operate with even greater intensity in the confined spaces of an interstellar vessel. Social structures would face unprecedented challenges, with no historical precedent for solutions. How do you maintain democratic governance across generations when founding principles become ancient history to later inhabitants? The original crew chose to undertake the mission. Their grandchildren did not. How do you maintain legitimacy for institutions established by people no one living ever met? How do you prevent authoritarian takeover when no external check on power exists? Every historical tyranny was eventually constrained by external forces. Neighbors invaded. Trading partners imposed sanctions. Internal factions received outside support. A generation ship has no neighbors, no trading partners, no external factions that might support internal resistance. A dictatorship established aboard a generation ship could persist indefinitely, with no mechanism for overthrow. How do you adjudicate conflicts when no appeal to outside authority is possible? Every legal system ultimately relies on some external legitimation. Divine authority, natural law, constitutional foundations established by previous generations. A generation ship must create and maintain legitimacy purely from internal resources across timescales that have destroyed every similar attempt in human history. Resource allocation creates additional stress that compounds across generations. Closed-loop systems inevitably experience inefficiencies and losses. No recycling system operates at perfect efficiency. Small losses compound over decades into significant shortages. Maintenance requirements consume increasing proportions of available labor as systems age and components wear. Systems designed for decades of operation fail after mere years, while anticipated replacements prove unavailable. Even if all social and psychological challenges were somehow overcome, no human-built structure has ever demonstrated such durability under operating conditions. Spacecraft in Earth orbit fail within decades. Space stations require constant resupply and repair from Earth. No closed system has ever operated continuously for a century without external support. Perhaps the answer lies in pausing biological time entirely. If human metabolism could be safely halted and later restarted, the passengers could effectively skip over the journey duration. They would close their eyes as Earth receded behind them and open them as Alpha Centauri approached. Subjectively, the journey would feel instantaneous, regardless of how many decades or centuries passed in the external universe. Cryogenic suspension, or cryonics, proposes cooling human bodies to temperatures where biological processes essentially stop. At liquid nitrogen temperatures roughly -196 degrees Celsius, chemical reactions proceed so slowly that years become effectively irrelevant. Cells neither age nor deteriorate. Time effectively stops for the frozen organism. Current cryonics technology can preserve isolated cells and small tissue samples. Reproductive medicine routinely freezes embryos for years before successful implantation. Blood banks store components for extended periods. Individual organs have been cooled and rewarmed with partial retention of function, but larger organisms consistently suffer catastrophic damage during freezing. Ice crystals form within cells, rupturing membranes and destroying delicate structures. The process of freezing itself damages the tissues that freezing is supposed to preserve. No mammal has ever been successfully frozen to cryogenic temperatures and revived to normal function. No human has ever been cryogenically preserved and restored to consciousness. The technical challenges scale with organism complexity. Human bodies contain trillions of cells that must all survive the freezing and thawing process. Blood vessels must remain intact to restore circulation. Neural connections that encode memory and personality must be preserved with fidelity, sufficient to restore the original person rather than creating a damaged copy. The revival process must somehow restart metabolic functions without cascading system failures. But suppose miraculous breakthroughs enabled safe human cryogenic suspension. Suppose passengers could be frozen at Earth departure and revived at Alpha Centauri arrival, decades or centuries later. Would this solve the timescale problem that renders interstellar travel impossible? Consider what happens during the journey, while the human passengers sleep frozen in their cryogenic chambers. The spacecraft must continue functioning. Navigation systems must maintain course across trillion-mile distances. Propulsion systems must execute planned maneuvers. The cryogenic chambers themselves must maintain precise temperatures for decades without interruption. Frozen humans cannot maintain their spacecraft. They cannot diagnose problems or implement repairs. They cannot adapt to unexpected situations or devise workarounds for failing systems. Every mechanical and electronic component must function flawlessly for centuries or repair itself without human assistance. More critically, what happens at destination? The arriving passengers must somehow revive without external assistance. Medical systems must operate after centuries of travel through radiation-saturated space. Automated equipment must diagnose each passenger and implement revival procedures that have never been tested at such timescales. The spacecraft must enter orbit or land using systems that have sat dormant for 100 years. And what about the civilization left behind on Earth? The launching society might not exist when the mission is scheduled to report success. The communication systems designed to receive transmissions might have been abandoned. The expertise needed to interpret mission data might have been lost in some civilizational disruption. Cryogenic suspension does not eliminate the civilization continuity problem. The frozen passengers become cargo whose survival depends on technology, maintaining itself across century-plus timescales without any human oversight or intervention. No technology has ever demonstrated such durability. No automated system has ever operated successfully for more than a few decades without human maintenance. The longest operating spacecraft in history, the Voyager probes have experienced numerous system failures across merely 50 years of operation. Perhaps the answer lies in removing humans from the spacecraft entirely during the journey. Artificial intelligence systems could theoretically operate indefinitely without biological constraints. Robot crews would not require food, water, or oxygen. They would not experience psychological stress from isolation. They would not die of old age or suffer the accumulated damage of cosmic radiation exposure. Advanced artificial intelligence could potentially manage spacecraft systems across century-plus timescales. Redundant processors could compensate for radiation damage to individual components. The mission could proceed without risking human lives during the dangerous journey phase. But AI crews face their own civilization continuity challenges that ultimately prove just as insurmountable as those facing human travelers. The artificial intelligence systems must be developed by human civilization. Their capabilities reflect the state of human technology at launch. They cannot upgrade themselves beyond their original design parameters without hardware modifications that require manufacturing capabilities unavailable during flight. An AI launched today would arrive at Alpha Centauri still running on technology that would be antique by arrival date. More critically, AI systems depend on physical hardware that degrades over time. Electronic components fail through accumulated radiation damage. Circuits develop shorts and opens. Mechanical systems wear out through friction and fatigue. Even the most durable robots would require repair and maintenance that becomes impossible across century-plus timescales without human support or manufacturing capability. And what happens when the AI arrives at Alpha Centauri? What civilization receives its reports? What human society interprets its findings and decides what actions to take based on discovered information? The purpose of interstellar exploration is expanding human knowledge and potentially human presence. If no human civilization exists to receive that knowledge, the entire mission becomes meaningless. AI crews do not eliminate the civilization continuity requirement, they merely shift it from the spacecraft to the receiving end. Someone must be waiting to learn what the machines discover. Someone must care about the results. Someone must have the capability to act on new information. A mission that departs Earth with great fanfare might arrive at Alpha Centauri to find that no one remembers it was launched. The civilization that sent it might have fragmented. The institutions that funded it might have dissolved. The communication systems might have been repurposed or abandoned. The AI might transmit its discoveries into a void where no one is listening. Every proposed technology ultimately fails against the same immovable barrier. We cannot engineer around this constraint because the constraint lies not in physics or engineering, but in the nature of human social organization itself. Nuclear pulse propulsion reduces journey times to centuries but still requires sustained commitment from unstable civilizations across timescales that exceed demonstrated human organizational capacity. The physics works. The engineering appears feasible. The civilizational requirement cannot be met. Antimatter engines face production and storage challenges that would require sustained research programs exceeding the duration of most nations. Even if these challenges were somehow overcome, the mission would still require civilizational support across journey times, measured in decades. The fundamental constraint remains unchanged. Laser sails cannot transport humans and still require decades of ground-based infrastructure maintenance. The launching facility must operate continuously. The tracking systems must persist. The receiving civilization must maintain capability and interest. Technology solves the propulsion problem, while leaving the civilization problem untouched. Generation ships relocate the civilization stability problem into a more constrained environment where failure becomes more likely rather than less. The ship becomes a tiny, isolated society, facing all the pressures that destroy earthly civilizations, compressed into confined spaces with no possibility of external support or escape. The approach does not solve the problem, it intensifies it. Cryogenic suspension shifts the burden entirely onto autonomous spacecraft systems that must operate for centuries without human maintenance. No technology has ever demonstrated such durability. The approach assumes capabilities that do not exist and shows no clear path to development. Even if the technology worked perfectly, the receiving civilization must still exist to make the mission meaningful. Artificial intelligence crews require human civilization to receive and utilize their discoveries. The purpose of exploration is expanding human knowledge. If no human civilization remains to receive that knowledge, the mission accomplishes nothing, regardless of what the machines discover. AI does not eliminate the civilization continuity requirement. It merely shifts the requirement from the spacecraft to Earth. No technology addresses the fundamental constraint. Interstellar distances are simply too large to cross within human civilizational timescales. We have reached a barrier that engineering cannot breach because the barrier is not made of physics. It is made of sociology and political science, and the accumulated evidence of thousands of years of human organizational failure. The next section examines the civilization problem directly. We will trace through the historical evidence showing why no mission requiring century-plus timescales can ever succeed regardless of technological capability. The barrier is not in our spacecraft, it is in ourselves. Human civilizations are temporary structures. This statement contradicts every narrative we tell ourselves about progress and permanence. We build monuments intended to last forever. We establish institutions designed to outlive their founders. We write constitutions meant to govern descendants we will never meet. We speak of eternal nations and timeless values and permanent achievements that will endure across the ages. Yet the historical record reveals an uncomfortable truth that demolishes these comforting illusions. No human civilization has ever maintained continuous coherent existence for more than approximately 2,000 years. Most civilizations endure far shorter periods before collapsing, fragmenting, or transforming beyond recognition into something their founders would not acknowledge as their creation. The journey to Alpha Centauri using optimistic propulsion concepts requires 100 to 150 years. Using currently achievable technology, the journey requires tens of thousands of years. Even the fastest conceivable spacecraft operating at the theoretical limits of known physics demand timescales measured in decades at absolute minimum. Every proposed interstellar mission requires that the launching civilization remain stable and committed throughout the mission duration. Every proposed mission requires that some civilization exist to receive the results and act upon the information gathered. Every proposed mission assumes continuity that the historical record suggests is impossible to guarantee. This section examines why no human civilization can provide the sustained support that interstellar missions require. The evidence draws from thousands of years of recorded history across every inhabited continent. The patterns repeat with disturbing consistency, regardless of geography or culture or technological level. The conclusion is unavoidable. Civilization continuity fails at precisely the timescales that interstellar travel demands. Consider the longest-lived continuous political entities in human history, and examine what their longevity actually demonstrates about human organizational capacity. The Roman civilization, in its various forms, endured approximately 1,000 years from the legendary founding of the Republic, around 500 BCE, to the fall of the Western Empire in 476 CE. This remarkable longevity exceeds most other political entities by substantial margins. Rome dominated the Mediterranean world for centuries and left cultural and legal legacies that persist to the present day. But even this extraordinary duration included massive transformations that challenge any notion of true continuity. The republic that expelled its kings bore little resemblance to the empire that deified its rulers. The Senate that governed through collective deliberation gave way to autocrats who commanded through military force. The religious foundations shifted from traditional Roman paganism through various mystery cults to official Christianity. The borders expanded to encompass the entire Mediterranean, then contracted under pressure from migrating peoples. The Rome of the 5th century shared a name with the Rome of the 5th century BCE, but operated as a fundamentally different society with different values, different structures, and different purposes. What lessons does Roman longevity offer for interstellar mission planning? Rome survived through continuous adaptation and transformation. The institutions of one century were dismantled and replaced by the next. The commitments of one emperor were repudiated by his successors. Long-term projects required continuous advocacy across generations, with no guarantee of continuation. The aqueducts and roads that Romans built required constant maintenance that ceased when the empire fragmented. Within centuries, these engineering marvels had deteriorated into ruins. The Byzantine Empire continued Roman traditions for another 1,000 years after the Western collapse. Constantinople maintained continuity of law and administration and claimed direct descent from the Caesars. But Byzantium operated as an entirely distinct civilization with Greek rather than Latin as its primary language. The territory shrank to a fraction of Rome's former extent. The culture evolved in directions that classical Romans would have found alien. Counting Byzantium as Roman continuity requires stretching definitions beyond useful meaning. A mission launched by the Roman Republic would arrive to find the Byzantine Empire unrecognizable as the same civilization. Ancient Egypt maintained cultural continuity for over 2,000 years, from the Old Kingdom around 2600 BCE to the conquest by Alexander in 332 BCE. This represents perhaps the longest period of continuous civilization in human history. The pyramids built by early dynasties remained standing throughout Egyptian history. Hieroglyphic writing persisted across millennia. Religious traditions maintained recognizable forms across dozens of generations, but Egyptian continuity included radical discontinuities that undermine any assumption of stable institutions across such timescales. Intermediate periods saw political fragmentation as central authority collapsed and regional powers competed for dominance. The first intermediate period lasted over a century as Egypt fractured into competing kingdoms. The second intermediate period saw foreign Hyksos rulers control northern Egypt for over 100 years. Foreign invaders, including the Nubians, the Assyrians, and later the Persians, conquered and ruled for extended periods. Most critically, for interstellar mission analysis, Egyptian continuity depended on geographic isolation that spacecraft cannot replicate. The Nile Valley provided natural boundaries that protected Egyptian civilization from the disruptions affecting other regions. The predictable annual flood enabled agricultural stability that supported continuous culture. Remove these environmental supports, and Egyptian civilization proved as fragile as any other. When Alexander's armies arrived, Egyptian independence ended permanently. The civilization continued in altered form, but never again controlled its own destiny. Chinese civilization claims even longer continuity, stretching back over 4,000 years to the legendary Xia dynasty. Chinese scholars point to continuous cultural traditions, including Confucian philosophy and bureaucratic governance, and written language that have persisted across millennia. This cultural continuity is genuine and impressive, but this continuity is cultural rather than political or institutional. Dynasties lasted at most a few centuries before collapse. The Han dynasty endured roughly 400 years, but included a period of interruption. The Tang dynasty lasted nearly 300 years. The Ming dynasty survived 276 years. The Qing dynasty lasted 268 years before revolutionary overthrow. The average Chinese dynasty survived roughly 300 years before being overthrown through rebellion or conquest. Periods of fragmentation separated unified empires as competing kingdoms warred for supremacy. The Three Kingdoms period following Han collapse saw China divided for nearly a century. The period between Tang and Song dynasties witnessed decades of division among competing states. Each transition brought violence and disruption that would have doomed any ongoing interstellar mission support. Foreign conquest by Mongols established the Yuan dynasty that ruled with different values and priorities than preceding Chinese dynasties. Manchu conquest established the Qing dynasty that again transformed governance in fundamental ways. Modern China shares Confucian philosophical traditions with ancient predecessors, but not continuous institutional existence. A mission launched by the Han dynasty would arrive to find the People's Republic unrecognizable as the same civilization. The language would have evolved. The governance would have transformed multiple times. The territorial extent would have shifted dramatically. Nothing resembling continuous institutional support could have persisted across such timescales. The pattern repeats across every region and era, with depressing consistency. Sumerian city-states endured centuries before conquest by Akkadian invaders. Greek polis flourished for a few hundred years before Macedonian domination transformed the political landscape. The Mayan classical period lasted roughly 6 centuries before mysterious collapse depopulated the great cities. The Khmer Empire dominated Southeast Asia for 600 years before decline and abandonment of Angkor. The Ottoman Empire ruled vast territories for 6 centuries before dissolution following World War I. The British Empire spanned the globe for roughly 2 centuries before decolonization reduced it to a handful of scattered territories. No political entity has ever maintained the kind of continuous institutional commitment that an interstellar mission would require across century-plus timescales. The organizations that exist today will not exist in recognizable form in 200 years. The nations funding space programs may not exist in a century. The institutions managing long-term projects will transform beyond recognition within decades. Understanding why civilizations fail reveals why interstellar missions cannot rely on civilizational support across the timescales involved. The causes of collapse are varied, but predictable. Every long-term human organization faces the same fundamental pressures that eventually tear it apart. These pressures operate regardless of technological sophistication or cultural values or governance structures. Political fragmentation occurs as factions compete for power within established structures. Regions seek autonomy from central authority. Classes conflict over resource distribution. Religious or ethnic divisions create fault lines that eventually crack into open rupture. Generational transitions bring new leaders with new visions who dismantle the work of their predecessors. The United States has existed as a continuous political entity for approximately 250 years. This represents remarkable stability by historical standards. The Constitution has provided a framework for governance across nearly 2.5 centuries of dramatic change. The federal structure has survived civil war and depression and world wars and social upheaval. Yet during this period, the nation fought a devastating civil war that killed more Americans than all other conflicts combined. Political polarization today approaches levels not seen since that existential crisis. Fundamental disagreements about the nature and purpose of government divide the population into hostile camps. 250 years represents roughly 1/4 of the minimum journey. Time for advanced propulsion systems to reach Alpha Centauri. The United States has nearly torn itself apart multiple times within this span. Economic collapse destroys the surplus wealth that supports ambitious projects. Civilizations require excess production beyond immediate survival, needs to fund infrastructure and military forces, and cultural achievements and scientific research. Economic downturns eliminate this surplus. Priorities shift toward immediate survival. Long-term projects lose funding as resources redirect toward urgent needs. The 2008 financial crisis nearly collapsed. The global economic system, despite decades of institutional safeguards designed to prevent exactly such catastrophic failures, millions lost homes and savings. Governments spent trillions preventing complete systemic collapse. Complete recovery required nearly a decade of painful adjustment. Such disruptions occur regularly throughout history, with varying severity. Any interstellar mission requiring century-plus support would face multiple such crises guaranteed by the cyclical nature of economic systems. Resource depletion undermines the material foundation of complex societies. Civilizations consume the resources that enable their existence. Forests become farmland, become deserts. Aquifers drain dry as irrigation extracts water faster than rainfall replenishes it. Mineral deposits exhaust as easily accessible ores give way to increasingly difficult extraction. Topsoil erodes as intensive agriculture strips the land of fertility. The infrastructure supporting advanced technology depends on continued resource availability that cannot be guaranteed across century timescales. Rare earth elements essential for electronics come from limited deposits. Fossil fuels that power current civilization are finite and declining. The materials required to build and maintain interstellar spacecraft might not remain available across the timescales such missions require. Environmental degradation compounds resource problems in ways that threaten civilizational survival. Civilizations alter their environments in ways that eventually undermine their own foundations. The Fertile Crescent that birthed Western civilization is now mostly desert, transformed by millennia of irrigation and overgrazing. Deforestation has converted regions from productive forest to barren scrubland across every inhabited continent. Climate change threatens agricultural systems worldwide in ways that could trigger civilizational collapse within decades. War and conquest destroy existing structures and replace them with new organizations that may not honor previous commitments. Every major civilization in history has faced invasion or attempted conquest or internal warfare. Political boundaries shift as armies advance and retreat. Institutions are dissolved by victorious enemies. Accumulated knowledge disperses as scholars flee or die. The victors rarely maintain their predecessors' projects. They have their own priorities and their own ambitions. A mission launched by one empire might arrive during the reign of its conquerors, who have no interest in honoring commitments made by defeated enemies. The tracking stations might be destroyed in warfare. The communication systems might be repurposed for military needs. The personnel with relevant expertise might have fled or been killed, or simply reassigned to more pressing tasks. Technology disruption transforms societies faster than institutions can adapt. The Industrial Revolution completely restructured human civilization within 2 centuries. Agricultural societies became industrial societies. Rural populations became urban populations. Traditional crafts became factory production. Social relationships transformed as old patterns gave way to new economic realities. The digital revolution is transforming civilization again within decades. Manufacturing is becoming automated. Services are becoming algorithmic. Communication is becoming instantaneous and global. Any institution designed for current conditions will become obsolete before century-plus missions complete. The organizations managing interstellar missions will need to adapt to technological changes that cannot be predicted from the launch date. The historical record provides abundant examples of projects and infrastructure that seemed permanent but proved fragile across timescales far shorter than interstellar missions require. The Library of Alexandria represented the ancient world's greatest repository of knowledge. For centuries, it collected and preserved manuscripts from across the Mediterranean world. Scholars traveled from distant lands to study within its walls. It seemed like an institution that would last forever. Yet the library declined through a combination of reduced funding and political neglect, and occasional violence until its collections dispersed and its buildings fell into ruin. No single catastrophic event destroyed it. Accumulated neglect across a few centuries accomplished what conquest could not. The Roman road system represented perhaps the greatest infrastructure achievement of the ancient world. 50,000 miles of paved highways connected every corner of the empire. These roads facilitated commerce and military movement and communication across vast distances. They were built to last forever, using techniques that modern engineers still admire. Yet within centuries of the empire's fall, the roads had deteriorated into fragments. Medieval Europeans travelled along remnants that reminded them of past glories, without the ability to maintain or replicate such engineering. The Gothic cathedrals of medieval Europe were built to stand until the end of time. Generations of craftsmen devoted their lives to construction projects they knew they would never see completed. Some cathedrals required 2 centuries or more to finish, yet many remain incomplete to this day. Funding dried up. Priorities shifted. Wars intervened. The institutional commitment required to complete these relatively simple building projects could not be maintained across the timescales required. The Concorde supersonic passenger jet represented the pinnacle of aviation technology when it entered service in 1976. It cut transatlantic flight times in half. It seemed like the obvious future of air travel, yet the Concorde program was cancelled in 2003 after less than 30 years of operation. Rising costs and a fatal crash and declining passenger interest doomed what had seemed like an inevitable technological advance. The capability to fly passengers at twice the speed of sound was deliberately abandoned and has not been recovered 2 decades later. The Space Shuttle was designed for a 30-year operational life and achieved it, but the program was cancelled without a replacement ready. For nearly a decade after the final shuttle flight, the United States lacked the capability to launch astronauts into space using domestic vehicles. The most technologically advanced nation in human history could not maintain continuous human spaceflight capability across a single decade of transition. An interstellar mission requires continuous support from the launching civilization across timescales that exceed any demonstrated human organizational capacity. Communication systems must operate throughout the journey duration. Ground-based facilities must track the spacecraft and receive its transmissions. Personnel must be trained to interpret data across generational transitions, as older experts retire and younger specialists must be recruited. Funding must survive political and economic disruptions that historically have derailed far less ambitious programs. Consider what continuous support actually means across a 150-year mission to Alpha Centauri using optimistic propulsion assumptions. The mission control facilities must operate without interruption for a century and a half. No scientific facility has ever demonstrated such operational longevity. The oldest continuously operating observatory dates to the 18th century, but has experienced numerous closures and interruptions and technological overhauls that would disrupt mission continuity. Equipment has been replaced multiple times. Staff has turned over dozens of times. Funding has fluctuated with economic and political conditions. Continuous uninterrupted operation for 150 years exceeds anything the historical record demonstrates is possible. The Greenwich Observatory was founded in 1675 to support British naval navigation. It operated continuously for over 3 centuries before relocating due to light pollution from expanding London. Even this remarkable institutional longevity included multiple reorganizations and funding crises, and changes in mission that would be incompatible with supporting an ongoing interstellar mission. The trained workforce must transfer institutional knowledge across 5 to 7 generations of personnel. The engineers who design the mission will be dead long before it completes. Their students will train successors who will train successors who will train successors. Each transition risks loss of critical knowledge. Each generation must reconstruct understanding from incomplete records. No organization has ever maintained such knowledge transfer for purely technical projects across such timescales. Religious institutions and cultural traditions persist across such timescales, but they operate through fundamentally different mechanisms than technical mission support. Religious knowledge transfers through ritual and narrative and emotional commitment. Technical knowledge requires precise documentation and practical training and hands-on experience with specific equipment. The methods that preserve religious traditions across millennia do not work for engineering expertise. Consider what happened to the knowledge required to build Saturn V rockets. Within decades of the Apollo program's cancellation, much of the practical expertise had been lost. Engineers retired or died. Documentation proved incomplete. Tacit knowledge that existed only in the minds of experienced workers vanished with those workers. Rebuilding the capability to launch similar missions would require essentially starting over, despite the existence of blueprints and specifications. The funding stream must remain stable through economic cycles and political transitions, and shifting priorities that historically have disrupted far shorter programs. No government program has ever maintained continuous funding for a century. The James Webb Space Telescope required 30 years from initial concept to launch and experienced multiple near cancellations due to budget disputes. The International Space Station required continuous international cooperation across more than 2 decades of construction and operation. Even this relatively modest timeframe proved challenging. Partner nations repeatedly threatened withdrawal over political disputes unrelated to the station itself. Funding crises delayed construction as participating governments faced competing domestic priorities. Technical problems required costly redesigns. The station will be deorbited after roughly 30 years of operation because the cost of maintaining aging systems has become unsustainable. 30 years of continuous operation represents a remarkable achievement, yet falls far short of the century-plus commitment interstellar missions require. The Hubble Space Telescope provides another instructive example. This remarkable instrument required servicing missions approximately every 3 years to replace failed components and upgrade capabilities. Without these regular interventions, the telescope would have ceased functioning within a decade of launch. An interstellar spacecraft cannot receive servicing missions. It must operate for 10 to 15 times longer than Hubble, with zero possibility of repair or upgrade from external sources. The communication infrastructure must survive whatever disruptions occur on Earth during the mission. Radio telescopes require maintenance, antenna systems require repair, power systems require fuel or connection to functioning electrical grids. Personnel require salaries and housing and all the support structures that modern technical workers expect. Any breakdown in this chain ends the mission regardless of spacecraft status. What happens when economic depression eliminates the budget for mission support? What happens when war destroys the tracking facilities? What happens when political revolution brings to power a government hostile to the previous regime's projects? What happens when technological change renders the communication systems obsolete? What happens when no one remembers why the mission was launched or cares about its results? Even if Earth-based civilization remained perfectly stable, communication delays would render mission support increasingly difficult across interstellar distances. Signals traveling at light speed require 4.37 years to cross between Earth and Alpha Centauri. A message sent from the spacecraft would require nearly 9 years for ground controllers to receive it and formulate a response and transmit that response back to the spacecraft. Interactive communication becomes impossible. Every action must be planned years in advance, with no possibility of real-time adjustment. For a spacecraft experiencing an emergency, 9 years represents an eternity. Systems fail within hours or days. Situations evolve within weeks or months. By the time Earth learns of a problem and sends instructions, the problem has either resolved itself or destroyed the mission. The crew cannot wait 9 years for advice on how to handle a life support failure. The automated systems cannot pause for a decade while engineers on Earth diagnose a navigation error. This communication delay means that spacecraft must operate autonomously for extended periods, regardless of what support structures remain on Earth. Every critical system must be designed for independent operation without human oversight. Every failure mode must be anticipated and addressed through onboard automation. Every contingency must be planned before launch because no assistance will be available during the journey. No spacecraft has ever demonstrated such robust autonomous capability across the timescales interstellar travel requires. All successful space missions have relied on continuous ground support for problem solving and course corrections. The Mars rovers receive daily commands from Earth. The Voyager probes transmit data that engineers analyze to plan subsequent operations. Even highly autonomous systems depend on periodic human intervention to handle unexpected situations. But suppose perfect autonomous spacecraft could be built. Suppose communication delays posed no operational obstacles. The civilization continuity problem remains unchanged. Someone must be waiting to receive the spacecraft's discoveries. Someone must be capable of understanding and utilizing the information gathered. Someone must care enough to be listening when the transmissions arrive. A mission arriving at Alpha Centauri after 150 years might find that no one on Earth remembers it was launched. The civilization that sent it might have fragmented into competing states that lost the technical capability to receive interstellar transmissions. The knowledge needed to interpret mission data might have been lost in some civilizational disruption. The institutions that funded the mission might have been abolished by revolutionary governments. The tracking stations might have been destroyed in warfare, or dismantled for resources, or simply abandoned when funding ran out. Consider the mathematics of civilizational stability across interstellar timescales and what probability analysis reveals about mission success. Human civilizations face disruption on timescales measured in decades. Major political disruptions occur roughly every 20 to 50 years as governments change and revolutions occur and wars reshape political boundaries. Major economic crises occur roughly every 10 to 20 years as business cycles oscillate and financial systems periodically collapse. Major technological disruptions occur roughly every 30 to 50 years as new technologies transform societies faster than institutions can adapt. A 150-year mission must survive through 3 to 15 major political disruptions, depending on their frequency and severity. It must weather 5 to 15 major economic crises that threaten funding and institutional stability. It must adapt to 3 to 5 major technological transitions that render original equipment and methods obsolete. The probability of maintaining continuous institutional support through all these disruptions approaches zero, based on historical evidence. This is not pessimism. This is pattern recognition from thousands of years of human history across every inhabited continent and every cultural tradition. Every generation believes its institutions are special and permanent. Every generation believes it has solved the problems that destroyed previous civilizations. Every generation is wrong. The mission that launches next decade may find its support infrastructure dismantled by political opponents 20 years later. The agency managing it may be eliminated in a budget crisis as economic priorities shift. The nation funding it may fragment into successor states that repudiate previous commitments. The civilization anchoring it may collapse under pressures that seem unimaginable today, but have destroyed countless previous societies. The generation ship, or cryogenic vessel or AI probe that departs with such hope and ambition may arrive at Alpha Centauri to find that no one is listening. The triumphant message announcing arrival at another star may echo across the void forever unanswered. The greatest achievement in human exploration may be forgotten by a civilization that no longer remembers why it mattered. All of this still fails because even if we could somehow guarantee civilization stability on Earth, the crew themselves face the same organizational pressures. A generation ship is just a tiny civilization facing all the same fragmenting forces in a far more constrained environment. The social dynamics that tear apart earthly civilizations would operate with even greater intensity in the confined spaces of an interstellar vessel. The isolation would be absolute, the resources would be finite, the pressures would be unrelenting. The same political fragmentation and economic stress and social conflict that destroy earthly civilizations would destroy shipboard civilizations even faster. The generation ship does not escape the civilization continuity problem. It concentrates and intensifies it. No matter how advanced the technology becomes, the fundamental constraint remains unchanged. Interstellar distances require journey times that exceed the demonstrated stability limits of human social organization. We are attempting to solve an engineering problem that is actually a sociological problem with no known solution. We are trying to build spacecraft that can outlast the civilizations that build them. We are trying to maintain commitment across timescales that exceed human organizational capacity. The technology is not the limiting factor. Physics permits interstellar travel. Engineering can design spacecraft capable of surviving the journey. Propulsion systems can achieve velocities that reduce travel times to centuries rather than millennia. But none of this matters if no civilization remains stable enough to launch the missions. None of it matters if no civilization survives to receive the results. None of it matters if the fundamental constraint of human organizational capacity renders every mission impossible, regardless of technical achievements. The next section examines what this means for humanity's relationship with the cosmos. The stars will remain forever beyond our reach. Not because we lack the technology to get there, but because we lack the civilizational stability to complete the journey. This conclusion has profound implications for how we understand our place in the universe and what we can hope to achieve as a species. We have traced the journey to Alpha Centauri through physics and engineering, through propulsion systems and life support through history and political science. Every path leads to the same immovable barrier. The stars lie beyond our reach, not because we lack the technology to get there, but because we lack the civilizational stability to complete the journey. This conclusion challenges deeply held beliefs about human potential. We tell ourselves that any problem can be solved with sufficient ingenuity. We believe that obstacles exist only to be overcome. The entire narrative of human progress celebrates our capacity to transcend limitations that once seemed permanent. We crossed oceans that ancient sailors believed marked the edge of the world. We flew through skies that our ancestors thought belonged only to birds and gods. We walked on the moon that poets had used for millennia as a symbol of the unreachable. Yet the cosmos imposes constraints that transcend human ambition. The speed of light places absolute limits on communication and travel that no technology can circumvent. The distances between stars create isolation that no engineering can fully bridge. The timescales required for interstellar journeys exceed the demonstrated stability of human civilization by margins so vast that hope itself seems irrational. Let us calculate the probability that a civilization could successfully complete an interstellar mission to Alpha Centauri using the most optimistic assumptions that serious physics permits. Assume advanced propulsion technology, enabling journey times of 100 years. This requires nuclear pulse propulsion, or something comparably ambitious, operating flawlessly across a century of travel. Assume perfect spacecraft engineering requiring no maintenance failures that exceed onboard repair capabilities. Assume ideal crew selection, preventing psychological breakdown despite a century of isolation in the most hostile environment humans have ever attempted to survive. Assume successful cryogenic suspension if the mission design requires passengers to sleep through the journey, eliminating biological aging and resource consumption during transit. Even with all these optimistic assumptions, the mission still requires the launching civilization to maintain institutional support for 100 years. Ground stations must track the spacecraft. Communication systems must remain operational. Personnel must be trained across generational transitions. Funding must flow continuously through economic cycles and political changes. Based on historical evidence, the probability that any major institutional project survives 100 years without fundamental disruption is approximately 10 to 15%. Consider the projects that have attempted such longevity. Consider how few have succeeded. Consider how many have been abandoned or transformed beyond recognition within far shorter timescales. The historical record provides no basis for confidence in century-scale institutional continuity. The mission still requires the receiving civilization to exist in a form capable of utilizing the returned information. Someone must be listening when the spacecraft reports its discoveries. Someone must possess the technical capability to receive and interpret interstellar transmissions. Someone must care about results from a mission launched by their great-great-grandparents. The probability that Earth-based civilization remains technologically capable and interested in interstellar discoveries 100 years from now is perhaps 50%. This estimate may be optimistic, given the disruptions that human societies routinely experience across such timescales. Wars and revolutions and economic collapses and technological transformations could easily render the receiving civilization incapable of or uninterested in mission results. Multiply these probabilities together. The likelihood that both conditions are met approaches 5 to 7%, a 93 to 95% probability of mission failure, not from technical causes, but from civilizational instability. The spacecraft might function perfectly. The crew might survive in excellent health. The scientific instruments might gather extraordinary data, and none of it would matter because no one would be waiting to receive the transmission. Now extend the timeline to more realistic propulsion capabilities. A 500-year journey faces 5 major civilizational cycles based on historical patterns of rise and fall. A 1,000-year journey faces 10 such cycles. The probabilities compound exponentially towards zero with each additional century of required stability. Even accounting for optimistic assumptions, the mathematics reveals that successful interstellar missions are extraordinarily unlikely, not merely difficult, not merely expensive, not merely requiring unprecedented commitment, extraordinarily unlikely to succeed regardless of technological investment, because the fundamental constraint lies outside the domain where technology operates. This is why no human will ever reach Alpha Centauri. Not because we cannot build the ships, not because we cannot survive the radiation or the isolation or the psychological stress, because we cannot maintain the civilizational coherence that mission success requires. The barrier is not in our machines, it is in ourselves. Every technological proposal ultimately fails against the civilization continuity problem, regardless of how ingeniously it addresses the engineering challenges. Nuclear pulse propulsion reduces journey times to decades or centuries, but still requires sustained commitment from unstable civilizations across timescales that exceed demonstrated human organizational capacity. The physics works. The engineering appears feasible. Antimatter engines face production and storage challenges that would require sustained research programs exceeding the duration of most nations. Even if these challenges were somehow overcome, the mission would still require civilizational support across journey times measured in decades. The fundamental constraint remains unchanged. Laser sails cannot transport humans and still require decades of ground-based infrastructure maintenance. The launching facility must operate continuously. The tracking systems must persist. The receiving civilization must maintain capability and interest. Technology solves the propulsion problem while leaving the civilization problem untouched. Generation ships relocate the civilization stability problem into a more constrained environment where failure becomes more likely rather than less. The ship becomes a tiny, isolated society facing all the pressures that destroy earthly civilizations, compressed into confined spaces with no possibility of external support or escape. The approach does not solve the problem. It intensifies it. Cryogenic suspension shifts the burden entirely onto autonomous spacecraft systems that must operate for centuries without human maintenance. No technology has ever demonstrated such durability. The approach assumes capabilities that do not exist and shows no clear path to development. Even if the technology worked perfectly, the receiving civilization must still exist to make the mission meaningful. Artificial intelligence crews require human civilization to receive and utilize their discoveries. The purpose of exploration is expanding human knowledge. If no human civilization remains to receive that knowledge, the mission accomplishes nothing, regardless of what the machines discover. AI does not eliminate the civilization continuity requirement. It merely shifts the requirement from the spacecraft to Earth. No technology addresses the fundamental constraint. Interstellar distances are simply too large to cross within human civilizational timescales. We have reached a barrier that engineering cannot breach, because the barrier is not made of physics. It is made of sociology and political science, and the accumulated evidence of thousands of years of human organizational failure. Alpha Centauri marks merely the closest boundary of cosmic isolation. Beyond our nearest stellar neighbor, the distances grow rapidly, and the required journey times expand beyond even the most generous estimates of civilizational durability. The next nearest star, Barnard's star, lies 6 light-years away. At the velocities achievable through nuclear pulse propulsion, the journey would require approximately 200 years. The next nearest Sun-like star, Tau Ceti, lies 12 light-years distant, requiring journeys measured in centuries even with optimistic propulsion assumptions. The nearest star known to host potentially habitable planets beyond Proxima Centauri requires even longer journeys, stretching toward timescales that make even century-duration missions look achievable by comparison. Even if we could somehow reach Alpha Centauri, the next destination would prove proportionally more difficult. Each step outward into the galaxy faces multiplied timescales and multiplied civilization stability requirements. The mathematics that renders Alpha Centauri unreachable renders more distant stars exponentially more impossible. The Milky Way contains 400 billion stars scattered across a disk, 100,000 light-years in diameter. Earth-like planets likely number in the billions based on observations of planetary systems around nearby stars. Alien civilizations may have arisen countless times across the billions of years of galactic history. Yet the distances separating stellar systems create isolation that renders meaningful contact effectively impossible. Any alien civilization facing similar constraints would reach the same conclusion we have reached. Interstellar travel requires civilizational stability that evolved social species apparently cannot maintain. The stars remain forever beyond reach, not because physics forbids the journey, but because biology produces civilizations that cannot sustain the effort required. This may explain the silence that greets our searches for extraterrestrial intelligence, despite billions of years of galactic history, during which alien civilizations could have arisen and spread across the stars. It is not that intelligent life is rare, it is that intelligent life cannot cross the interstellar voids to establish contact with neighboring civilizations. Each intelligent species arises in isolation, flourishes briefly on its home world and vanishes without ever meeting its cosmic neighbors. The Fermi paradox asks why we have not detected evidence of alien civilizations given the vast number of stars and the long history of the galaxy. Perhaps the answer lies not in the rarity of intelligence, but in the impossibility of interstellar expansion. Every civilization reaches the same barrier we have identified. Every civilization discovers that the timescales required for interstellar travel exceed the timescales available before civilizational collapse. The galaxy may be filled with the ruins of civilizations that reached for the stars and failed. Abandoned generation ships drifting between stars, their crews long dead from social collapse or system failure. Silent probes that completed their journeys to find no one listening for their reports. The wreckage of ambitions that exceeded organizational capacity scattered across the void as monuments to universal futility. Or perhaps no ruins exist because no civilization ever launched the missions that would create them. Perhaps every intelligent species recognizes the impossibility before committing resources to doomed efforts. Perhaps we are unusual only in our persistent hope that somehow we will prove different from every other civilization that has ever existed. The impossibility of interstellar travel reveals something profound about human existence and our place in the cosmic order. We evolved on a single planet orbiting a single star. Our biology is adapted to Earth conditions with narrow tolerances for temperature and pressure, and radiation and gravity. Our psychology is shaped by earthly environments with their horizons and seasons and weather, and the daily rhythm of light and darkness. Our social structures are products of terrestrial evolution, operating across geological timescales in competition and cooperation with other humans and other species. Nothing in this evolutionary heritage prepared us for the cosmos. We did not evolve to comprehend trillion-mile distances or million-year timescales. We did not evolve to maintain stable civilizations across centuries. We did not evolve to survive in environments hostile to every biological process that sustains us. The stars shine in our night sky like beacons promising destinations we will never reach. They are reminders of a universe that cares nothing for human ambition. They mark boundaries that we can observe but cannot cross. They represent possibilities that will remain forever theoretical, regardless of how much we might wish otherwise. This conclusion is not cause for despair, despite the finality it implies for our cosmic ambitions. The impossibility of interstellar travel does not diminish the significance of human existence. We remain the only known intelligence capable of contemplating these questions. We remain the universe. Becoming aware of itself through biological evolution and cultural development, even if that awareness is confined to a single stellar system. Earth is our home. Solar system is our neighborhood. These boundaries may be permanent fixtures of human existence rather than temporary limitations awaiting technological solutions. The resources and wonders available within our cosmic backyard exceed anything we will ever fully explore or comprehend across the entire future history of our species. Mars awaits exploration and perhaps settlement. The moons of Jupiter and Saturn harbor oceans that might contain life. The asteroid belt contains resources that could support civilizations far larger than Earth alone permits. The outer solar system extends billions of miles, offering frontiers that would require millennia to fully explore. We need not reach the stars to find adventure and discovery and expansion sufficient for countless generations. Perhaps the impossibility of interstellar travel contains a hidden gift that our disappointment prevents us from recognizing. Perhaps it encourages us to focus on the world we actually inhabit, rather than dreaming of worlds we can never reach. Perhaps it reminds us that our true challenges lie not among the distant stars, but here on the planet that birthed us and the solar system that contains us. Human civilizations collapse because we cannot sustain the cooperation and commitment required for projects spanning centuries. This same limitation prevents interstellar travel. It also threatens our capacity to address existential challenges much closer to home that demand sustained effort across generations. Climate change requires coordinated action across decades to prevent catastrophic consequences. The same civilizational instability that prevents interstellar travel threatens our ability to maintain climate commitments across the timescales required. Governments change and priorities shift, and agreements made by one generation are abandoned by the next. Pandemic disease requires sustained investment in public health, infrastructure, and research capabilities that must persist through periods when no pandemic seems imminent. The same institutional fragility that would doom interstellar missions threatens our ability to maintain pandemic preparedness across decades between outbreaks. Nuclear proliferation requires permanent vigilance and sustained diplomatic effort to prevent catastrophic use of weapons that could end civilization entirely. The same political instability that renders century-scale projects impossible threatens our ability to maintain nuclear security across the decades and centuries required. If we cannot maintain focus on protecting our only planet, how could we ever maintain focus on reaching another star? The interstellar barrier reflects limitations that threaten us far more immediately than the impossibility of reaching Alpha Centauri. The same organizational failures that would doom generation ships could doom our civilization to collapse on Earth long before the stars become relevant. Alpha Centauri will continue shining 4.37 light-years away, regardless of human observation or ambition. Whatever wonders exist, there will remain unknown to human explorers forever. This permanence challenges our narratives of progress, but does not negate the value of human existence. We are not diminished by our confinement to a single stellar system. We are not failures because we cannot reach the stars. We are simply what we are. A species evolved on one world, adapted to one environment, capable of extraordinary achievements within our domain, but bounded by limitations written into the fabric of our biology and sociology. Every proposed solution to interstellar travel ultimately fails against the immovable barrier of civilization continuity. Generation ships require stable, isolated civilizations lasting longer than any isolated community has ever survived. Cryogenic suspension requires autonomous spacecraft operating for centuries without human maintenance, exceeding any demonstrated technological durability. Advanced propulsion still requires decade to century timescales that exceed institutional commitment capabilities demonstrated anywhere in human history. Artificial intelligence crews require human civilization to receive and interpret their discoveries, making the entire enterprise dependent on continuity, regardless of spacecraft autonomy. No matter how advanced the technology becomes, the fundamental constraint remains unchanged. We are a species whose civilizations rise and fall in cycles, measured by centuries at most. The stars require commitments measured in millennia at minimum. This is why no human will ever reach Alpha Centauri, not because physics forbids it. The physics permits interstellar travel at velocities that would reduce journey times to centuries. Not because engineering fails. The engineering challenges, while immense, appear solvable with sufficient investment and development. Not because biology cannot adapt. Humans can survive in space with appropriate life support and protection from radiation. Because human civilizations cannot remain coherent long enough to complete the journey. The barrier lies not in our technology, but in our nature. The limitation is not physical, but social and political and organizational. The cosmos has revealed its deepest truth through our analysis of interstellar travel. The universe is not hostile to human expansion. It is simply indifferent. The distances between stars create natural isolation that evolved civilizations apparently cannot overcome. The timescales required exceed the timescales available. The commitment demanded exceeds the commitment possible. We stand on our tiny world gazing at uncrossable chasms that appear deceptively small when measured in light years, but prove infinitely vast when measured in human organizational capacity. The stars remind us that we are fundamentally local creatures. We evolved here. We belong here. Our destiny lies not among distant suns, but here, on the planet that made us and the solar system that contains us. This is both our limitation and our opportunity. We cannot reach the stars, but we can learn to sustain our civilization across longer timescales than we have ever achieved. We can develop the institutional structures and cultural practices that extend human coherence beyond its historical limits. We can focus our ambitions on the challenges we can actually address, rather than dreaming of achievements that will remain forever impossible. Perhaps someday, our descendants will develop civilizational forms stable enough to contemplate interstellar journeys seriously. Perhaps they will find ways to maintain commitment across the millennia that cosmic distances require. Perhaps they will solve the organizational challenges that render such missions impossible for us. But that civilization would be so different from anything that has ever existed that calling it human strains the meaning of the word. The social structures required to maintain millennium-scale projects would bear no resemblance to any human society in history. The psychology required to sustain commitment across such timescales would represent a transformation of human nature more radical than any biological or technological modification we can imagine. The stars will remain forever out of reach for beings like us. Beings whose civilizations rise and fall within centuries. Beings whose institutions fragment and transform within decades. Beings whose commitments waver and redirect within years. And perhaps that is exactly as it should be. Perhaps the cosmos has established boundaries appropriate to our nature. Perhaps the interstellar void represents a fence around our yard, rather than a wall around our prison. Perhaps we have sufficient space within our solar system to achieve everything that beings like us can achieve. The universe has placed our nearest stellar neighbours at distances, requiring journey times that exceed the demonstrated stability of human civilization. Every technology fails against this fundamental constraint. Every solution proposed ultimately collapses back into the same impossibility. Alpha Centauri will continue shining beyond our reach, a permanent reminder of cosmic boundaries that human ambition cannot transcend, a beacon marking destinations we can observe but never visit, a symbol of all the wonders that will remain forever unknown because the distances are simply too vast and the timescales simply too long for beings whose civilizations measure their spans in centuries rather than millennia. No human will ever walk on a world orbiting those distant suns. No human eyes will ever see Alpha Centauri as more than a point of light in the night sky. No human hands will ever touch soil warmed by the light of another star. This is not a temporary limitation awaiting a clever solution. This is a permanent feature of human existence as fundamental as mortality itself. We are born and we die, and between birth and death we are confined to the single stellar system where our species evolved. The stars are beautiful. The stars are unreachable. The stars will shine on long after our civilization has joined all the others in the long silence of history. And perhaps there is peace to be found in accepting what we cannot change and focusing our energies on what we might actually achieve within the boundaries the cosmos has established for beings like us.